Hello everyone, I am going to deliver a lecture 1 common heat treatment processes. In this lecture I will cover the following topics. Here I will discuss the details about types of common heat treatment process. Here I will discuss whatever the common heat treatment process generally we used in welding process like preheating, interpass temperature control and post weld heat treatment process. That related details one by one I will discuss in this lecture. So, first of all type of heat treatment process, then I will discuss about the preheating process. In details I will discuss about this. Then in preheating process we will find some important topics that is related to hydrogen or cold cracking, then calculation of tau 8 by 5 and also how to calculate the preheat temperature. Apart from these things, if time permit, I will discuss about interpass temperature control related things also. In last lecture, I have already discussed about how to estimate the peak temperature in case of a point heat source and in case of a line heat source, that I have already discussed. So, what are the peak temperature estimated formulas we got from the previous lecture, that little bit I will discuss first. After that directly I will go to different types of common heat treatment processes. So, last lecture I have already discussed, that means outside the fusion boundary what is the peak temperature generally attained of a welding specimen or welded plate during its whole welding operation. How to estimate that thing? Using thin plate equation can be represented like this, and for thick plate case using point heat source can be represented like this. So, these things how it is coming I have already discussed, because in last lecture already detailed things I have already discussed. Here in this equation, you know, this T p is called as peak temperature. So, what is T p? T p is generally the peak temperature and T 0 is called generally initial temperature, and right side this Q is called net heat input, that is eta V I, and generally Y has is the distance from fusion boundary to away from the fusion boundary, that you can say. What does it means? Let us consider this is a welded specimen. So, let us consider this is the fusion zone. So, for a particular distance from this fusion zone boundary, particular point let us P. In this point P we want to find out what is the peak temperature attained during its whole welding operation. So, let this distance is generally represented as Y heat affected zone. Okay. Now, at this distance what is the peak temperature attained during its whole welding operation, that we can estimate for thin plate case using this equation number 1 you can say, and for thick plate case you can calculate this thing by using equation number 2. So, this equation have very wide application you can say. By this equation what are the things we can estimate? By this equation we can estimate first very important things, size of heat affected zone, heat affected zone, H A Z I am writing. So, it is also give you a idea about what is the effect of preheat temperature, or you can say T 0 or initial temperature. This is also sometimes called preheat temperature if we use preheating. So, it is also give you an idea what is the effect of preheat temperature, that means T 0 effect also this equation can provide. Apart from these things, this equation also will provide what is the effect of Q, that means net heat input, 1 heat affected zone size that also I will discuss little bit. So, from this equation itself, like let us first equation, from this equation itself one things you can observe that 1 by peak temperature T peak I am writing T peak minus T initial temperature I am writing T I or T 0 whatever it is you can say directly proportional to Y has heat affected zone size, as well as it is also you can say this is also inversely proportional to heat input Q. This you can see from this equation. So, from this equation one things you can observe that generally this heat affected zone size HZ will increase, you can say if your Ti is, what are the things, if Ti is increase, that means for a particular welding process, if now what is heat affected zone, you know heat affected zone means from fusion boundary to its recrystallization temperature. From fusion boundary to its recrystallization temperature is generally known as heat affected zone. So, let us consider the recrystallization temperature for mild steel case is around 270 degree centigrade temperature, whereas fusion boundary temperature generally is melting point temperature, it is let us 1540 degree centigrade temperature. Okay. So, 1540 degree centigrade temperature to 723 degree centigrade temperature, this region generally called heat affected zone size. So, from this equation one thing is very clear, if Ti increase then your heat affected zone distance, that means Y has is also increase. How? Because if Ti increase then because this if Ti increase then you can say this T p minus Ti will decrease, correct, this value will decrease. So, what are the things? So, we know 1 by T p minus Ti have a inverse effect with, that means heat affected zone. If this is decrease then this will increase definitely, that things here I am showing. So, this will decrease when, if we increase, if Ti is increase then Tp minus Ti, Tp means let us consider the fusion or heat affected zone boundary, let us Tp have a temperature that is 723 degree centigrade temperature, that is the heat affected zone boundary 723 degree centigrade temperature. Now, if Ti is increase, okay, then what happens, your this difference will decrease. If this difference will decrease then you can say your heat affected zone size, Y heat affected zone size will increase. That is I have written that heat affected zone size generally increase if preheat temperature increase. These things you should keep it in. How it is coming, you got the idea. Apart from these things, keeping all other parameter constant. So, if you increase the Q value, Q means net heat input, it is I have already written is net heat input, that is actually you can say eta V I, eta is the efficiency, V is the welding voltage, I is the current. So, if Q increase then you can say your Y value is, what are the things, your Y value will be increase. So, if Q increase then Y also, heat affected zone size also increase, this you should keep it in mind. How? So, net heat input increase means your heat affected zone increase, that things from this equation, this is equation number 4. So, from this equation number 4 itself you can got the idea, because this is actually you can say this Tp minus Ti is directly proportional to Q, or you can say your heat affected zone size, from this equation itself you can say your heat affected zone size is directly proportional to you can say Q, that also you can say from this equation, because if you bring Q in left side you will get Q is proportional to Y has. That is why for laser welding case, laser welding, electron beam welding, EB electron beam welding, plasma arc welding, for these types of high intensity heat source types of case, you can say your heat affected zone size is less. Generally laser beam, electron beam, then plasma arc welding, where generally high intensity of heat source is there generally your heat affected zone size is less. Why? Because in that case generally this Q value is less. Why? Q value is less compared to other arc welding process like submerged arc or SMAW welding process. Generally why it is comparatively lesser than submerged arc welding process, SMAW welding process in case of laser arc welding, because generally we know to melt the material, you can say there is required a particular heat flux. So, for high intensity beam means your heat is putting in a very small area. So, you see for a particular heat input Q, if it is put in a area A1, then whatever the what it is called area A1, and if the same heat input is putting in a area A2, then what happens? If this A1 is less than A2, then definitely this will be, if A1 is this, then what happens? This heat flux will increase. So, what does it means? What I want to say here, if net heat input is increased, your heat affected zone size is increased. So, for high intensity beam generally you should keep it in mind, your heat affected zone size is less, because a high intensity energy source result in a lower total heat input, because the energy used in melting the metal is concentrated in a small region. This you should keep it in mind. Like you see, to melt, here I am writing to melt the material. So, if this Q is in a small region, then this whatever the let us Q1 by A1. So, for to melt for another bigger size heat source, let us Q2 by A2 is required. Now, to melt generally this heat flux intensity should be same. So, let this should be equal to Q, this should be also equal to Q. Now, from here itself you can get the idea, if this A1, if A1 is increased, if A1 is increased, or if A1 is lesser, much lesser than A2, then you can say Q1 also much lesser than Q1 requirement, also much lesser than Q2. This you should keep it in mind. That is why in case of laser generally this area at which your heat sources fall, that area is very small. That means, in case of laser spot during welding, let us consider within a range of 2 millimeter diameter, whereas in case of submerged arc welding process, this diameter can be 10 mm, 2 mm and 10 mm. So, this 2 mm diameter, whatever the area it will have, this area will be let us A1, and this 10 millimeter diameter, whatever the area it will have, this area will be very high. What I am telling, understand, compared to this laser. Let this is your laser case, and this is let us arc weld, electric arc weld, let us submerged arc welding process. What I am telling, understand. That is why one thing, because but for melting purpose generally this heat flux requirement Q should be same for both the case, you can say. So, that is why the net heat input, this Q value in case of laser required is less due to its lower heat source size, and for arc welding process like submerged arc welding process, this Q requirement is higher because here generally this heat source size is comparatively bigger. That is why to get same heat flux Q, a small q, generally what happens, you can say your net heat input Q2 in case of arc welding process is much higher than you can say Q1. That is why I have already told you put this Q1 or Q2 is the net heat input. Generally this net heat input required in case of laser welding is comparatively lesser, because its intensity is higher compared to arc welding process, because its intensity in case of arc welding is lower. That is why always you should keep it in mind. In case here I have written, in case of laser welding process where high intensity beam is there generally you can say heat affected zone size is less in case of laser beam, electron beam, these types of welding process where intensity of the beam is high, whereas this heat affected zone size generally is more in case of bigger diameter heat source like submerged arc welding, SMAW, these types of arc welding process. This you should keep it in mind. Now, I am going to discuss about the very important common heat treatment processes which are widely used in the field of welding process. This heat treatment process is very common in case of low carbon alloy steel, which have a wide application in the field of what is called manufacturing industry. This low carbon alloy steel have a wide application, this issue. That is why what happens in this topics mainly I will focus on what are the common heat treatment process which are commonly used in commercially used steel plate and which have a wide application. Generally the heat treatment process which are used in single pass welding process is preheating and post weld heat treatment process. These two common heat treatment process generally used in case of single pass welding process. Single pass means if within a single run top and bottom reinforcement is achieved, then that is called generally single pass. Generally it is used for lower thickness types of plate case. This you should keep it in mind. That means here your weld bit geometry will be within single pass, you can get top and bottom reinforcement, means top bottom side you can single pass you can get. Now, in multi-pass types of welding process, they are required generally multiple number of parts to complete the welding process. This is generally used for thick types of plate. So, multi-pass welding process how it looks like? It look like let this 1 pass, 2 pass, 3 pass, 4 pass, 5 pass, 6 pass. Okay. These are the different paths generally we use in case of multi-pass welding. So, in case of multi-pass welding which is used for generally very thick section, in case of thick section generally this multi-pass welding process are used. Now, in case of multi-pass welding process we use different types of heat treatment process, like here also we use preheating as well as post weld heat treatment process. Apart from this thing there is required another controlling of interpass temperature. Interpass temperature means the temperature between two consecutive pass. Let this is pass number 1 and this is pass number 2. Let this is pass number 1 and this is pass number 2. So, in this two pass in between what should be the temperature? So, after that you should start your second pass. That means, after first pass how much cooling temperature is required, so that you can start this second pass, so that your structure will be defect free. That is called controlling the interpass. This is also very important temperature we need to control in the multi-pass welding process. Now, this common heat treatment process generally, what are the different types of process generally used to do this common heat treatment process? Generally for heating purpose we use, like here we generally use for getting preheating temperature, post weld heat treatment process we generally use either oven, or this can be done by resistance heating or by flame or torch heating. What I am telling, understand? That means these are the heat treatment process which is generally done by various operation, like by using of oven, by a resistance heater or by flame. And how we control the temperature which is required for preheating temperature, post well heat treatment temperature and interpass temperature. For controlling this temperature, we need to have some temperature detector. That temperature detector generally we use for controlling the temperature required for preheating, post well heat treatment as well as interpass temperature. We use generally either infrared camera or infrared gun. This is also called pyrometer. It is a non-conducting device. Okay. So, by using this gun you can detect the temperature in your required location to estimate what is called preheating temperature, post well heat treatment temperature as well as controlling the interpass temperature. Then you can also do it by using temperature indicated crayons. This is also have a important name, thermoplastics. This you should keep it in mind. This is a very important sticks generally here we use. So, here we generally use different types of sticks. That stick generally have a particular melting point. Okay. So, what happens that melting point generally retain on the stick cover. So, what happens once we during heating, once we put this stick over there, if the temperature goes beyond that melting point temperature of that stick, then that stick will create a liquid layer, okay, or you can say it can escape over there. If this stick temperature is higher than the temperature of that plate, then it will not create any escape on that plate. So, based on these things you can get a idea how much temperature is rising on the plate. Apart from these things you can use thermocouples also. Thermocouples you know, it is generally used two different types of alloying element. So, this is also called chromel, alumel types of material generally here we use. That thermocouple generally convert the temperature difference into voltage difference. That voltage difference generally we can calibrate with the help of data logging device. Okay. These are the very common what is called heat or temperature recording process, you know very well. So, I am not going to details about all these things. Okay. Now, these are the generally heating process as well as temperature control method generally we use to do this common heat treatment process. Generally in site for preheating purpose, electric stiff heater we use. Okay, this you should keep it in mind. Electric stiff heater is a very common practice in site for preheating purpose, because this preheating have a very important effect on weld quality. This you should keep it in mind, as well as for improving the weld ability. This you can say this preheating is also required in some case of steel material, especially for low alloy steel it is very common. So, one thing you should keep it in mind during use of electric stiff heater, this should be properly insulated to avoid danger of shock to welder. And for preheating of pipe, circular pipe, generally we use induction types of heating. This induction types of heating, how this induction types of heating is done? There generally we used around 60 hertz or 50 hertz types of transformer are there. By using this transformer, generally induction heating is done for 5 types of welded joint. Okay. Now, first of all I will discuss about preheating. So, what is preheating? So, in general low alloy steel is required to be preheated to some temperature prior to welding. So, before going to do welding of low alloy steel types of material, what we need to do? We need to do some preheating operation. Why this is required? This is very important things, that also I will discuss in subsequent slide. First of all I am just discussing, so that temperature at which generally this preheating is done on a pellet of low alloy steel is called preheating operation or preheating temperature, preheating operation temperature. always you should keep it in mind, generally it is suggested that preheating temperature should be above the 10 degree centigrade temperature of martensitic starting line, or you can say martensitic starting temperature. It should be above 10 degree centigrade temperature of martensitic starting temperature. So, it is suggested the technical community that preheating temperature, you can say T, you can say preheating, I am writing TPH should be equal to martensitic starting temperature plus approximately 10 degree centigrade temperature. This is the very common practice. Why? These things also I will discuss. Okay. This is required for common practice purpose. This you should keep it in mind. Now, what is martensitic starting temperature? I have already shown you this martensitic starting temperature. This is generally, you can say, in case of TTT diagram, I have discussed in detail about this martensitic starting temperature, because in left side curve, if you draw the TTT diagram, what you observe that this is time versus temperature. So, you observe that this curve is coming like this and right side curve is coming like this. Okay. So, this temperature, this horizontal temperature, whatever the temperature we got here, this is generally called martensitic starting temperature. In case of plain carbon steel, this temperature is a range of 220 degree centigrade temperature for mild steel types of material, you can say around. After that, generally here martensitic MS 50, that means martensitic transformation 50%, MS 90, these types of temperature line generally you can get, which is below this martensitic starting temperature. This you should keep it in mind. Now, so in case of low alloy steel, the temperature it is suggested should be above this martensitic starting temperature. And what is this above temperature range? It is around 10 degree centigrade above martensitic starting temperature. But in case of most low alloy steel, one thing you should keep it in mind, this martensitic starting temperature is quite higher side. But in case of mild steel, or you can say plain carbon steel, it is within that range around 220, but some low alloy steel, this temperature range is quite higher side, which generally making the welding at or above them somewhat uncomfortable to the welder. Okay. So, making welding at or above this martensitic starting temperature somewhat uncomfortable, you can say, to welder. Thereby, generally in these cases sometimes we need to potentially compromising the welding quality, because for such steel manufacturer generally often opt for this what it is called preheating temperature below martensitic start. Why? Due to this uncomfortable situation of welder, sometimes what it is called this temperature which generally use for preheating purpose, which can be below martensitic starting temperature for those steel whose martensitic starting temperature is higher side. So, one thing you should keep it in mind, where the temperature is generally minus some degree centigrade temperature. So, during winter time there can be a preheating temperature for doing welding operation generally used as low as 26 degree centigrade temperature. But in some plate also are there where there can be a preheating temperature 650 degree centigrade like for welding of ductile cast iron. Apart from these things, for highly hardenable steel, this temperature also can be 315 degree centigrade temperature also. What I am telling, understand? So, preheating temperature is depends on type of material which we are going to weld. For different types of material, it can have different level of preheating temperature. Like for highly hardenable steel, generally for high carbon the carbon nickel based steel, which have generally very higher martensitic starting temperature. Those case to improve weld quality generally, and this has also as high carbon percentage, that is why what happens there the preheating temperature range is higher side around 315 degree centigrade. For ductile cast iron where the carbon percentage is more than 3%, for those types of material also you see for preheating temperature is around 650 degree centigrade temperature. And in some other material like mild steel material, there can be a preheating temperature for mild steel for outdoor during winter time can be 26 degree centigrade temperature. But always you should keep it in mind, generally it is preferable if possible your preheating temperature should be around 10 degree centigrade higher than the what it is called martensitic temperature. This is preferable, this you should keep it in mind. Why this preheating temperature is required? Because preheating temperature is very much essential, because it has lot of effect. One of the most important effect is generally this preheating generally remove the moisture, if there will be any moisture in weld plate it is removed. It also remove the lubricants and other contaminants also it is removed. What are the other contaminants? The contaminants which generally the source of hydrogen it removes during welding operation from the weld zone. So, once it remove those things, it generally eliminate lot of what it is called adverse effect of welding process. What are those? Everything in one by one I will discuss. Most importantly, I have already shown you this preheating temperature generally what is called affect the cooling rate, because in case of thin plate you know I have already discussed these things. Cooling rate dT by dt is directly proportional to T minus T0 or you can say to the power cube, and for thick plate this is generally T minus T0 to the power square. What I am telling, understand? This is for thick plate. So, from this equation generally this T0 is called initial temperature, or this is you can consider as T preheating temperature. So, if this TPH increase, you can say your if TPH increase, then this difference of T minus T0 will decrease. So, you can say your dT by dt cooling rate will decrease. This you should keep it in mind. So, if preheating temperature increase, then cooling rate decrease. Cooling rate decrease means to cool the material it takes more time. What I am telling, understand, it takes more time. So, once it takes more time, so that is why what happens, it generally allow more time to what is called you can say escape or hydrogen removal. What I am telling, understand, it provide more time of hydrogen removal, because hydrogen generally have a critical effect on weld quality. What I am telling, understand, because this hydrogen generally creates some cracking types of phenomena in case of weld joint. How it is, everything in I will discuss. Okay. So, once the cooling rate is decreased, then what happens, it is what is called whatever the hydrogen generally entrapped inside the weld zone or surrounding of weld zone, heat affected zone, that is heat affected zone. So, it takes more time to escape. Then what happens, hydrogen related adverse effect, what happens is can be avoided by using or increasing the what it is called preheating temperature. Then that is why here I have written furthermore cooling rate generally reduction can affect austenite transformation to produce other than you see martensite. That means, if cooling rate increase, then from TTT diagram already you have seen, if cooling rate increase, then what happens? There is a chance of formation of martensite. But if cooling rate decrease, that means if it takes more time, from TTT diagram I have already shown, that means generally this martensite formation you can avoid. That is why if you increase the preheat temperature or if you apply the preheat temperature, then what happens? You can avoid martensitic formation, because martensitic formation have a adverse effect on well quality. How it is, everything in details I will discuss. And another things you should keep it in mind, here I have written most low alloy steel that may be susceptible to hydrogen induced cracking transform from austenite during cooling through 800 to 500 degree centigrade temperature range. This you should keep it in mind. Generally 800 to 500 degree centigrade temperature range, this low alloy steel austenite transform to other phases like whether martensite, pearlite, bainite or ferrite, whatever the phases will be formed after cooling, that generally occurs within a temperature of 800 to 500 degree centigrade temperature. This you should keep it in mind. Mostly, you know, 500 degree centigrade temperature in case of TTT diagram is close to your nose temperature, you know, and 800 degree centigrade temperature above what is called critical lower critical temperature, you know, for steel in TTT diagram I have already shown. So, within this range, if we control the time, then generally we can control the formation of what it is called final microstructure of a weld joint. That is why this time between 800 to 500 degree centigrade temperature is a very important time, that is called one of the very important or critical time range, critical time T. That is why in case of welding, the length of time T, this time is represented by tau or T 8 by 5. T 8 by 5 means T 800 to 500 degree centigrade temperature, how much time second is required to reach, that generally affect the final microstructure of your weld zone. This you should keep it in mind. Not only weld zone and heat affected zone, especially in heat affected zone, because this heat affected zone generally microstructure generally changes within this temperature range drastically. Okay. So, that is why here I have written the length of time T 8 by 5 is still spent in this range during cooling will establish its microstructure and its susceptibility to cold cracking. This you should keep it in mind. That means, if the microstructure will be martensitic types, then it will be less susceptible for cracking. What I am telling, understand? That means, it will crack easily. If your microstructure will ferritic or pearlitic types of a structure apart from martensitic structure, then there is a less chance or it is more generally it is that its susceptibility to cracking is, you can say, more. What I am telling, understand? That means, its cracking resistance is more. That is why another point also I have written here, to maximize the cracking resistance, a microstructure that is free of untempered martensite is desired. That is, the austenite would have transformed to ferrite plus carbide and no austenite should be present when it is reached to what it is called reached to martensitic starting temperature. That means, no austenite should be present to transform from austenite to martensite. So, when it is reached to martensitic starting temperature, that things also I have written. So, no austenite will be available to transform to martensite upon reaching martensitic starting temperature. MS means martensitic starting temperature. This you should keep it in mind. What I am telling, understand? So, before martensitic starting temperature, all martensite should be converted to other phases like ferrite plus carbide I have already written, that is pearlitic types of a structure. What I am telling, understand? Now, here I have already discussed in previous slide about what is called the term called cracking. What is cold cracking? So, cold cracking generally is a phenomena of hydrogen embrittlement phenomena. So, cold cracking is a hydrogen embrittlement phenomena that occurs after cooling of welded specimen. That means, the welding is done. After welding, if you keep the welded specimen for some hours, even some days also, it will observe that after some hour or some days there occurs some cracking. That cracking generally starts from heat affected zone and its propagate transverse to the welding direction zones. What I am telling, understand? Just a simple illustration of this cold cracking here I am showing. So, this you can see it is started at generally heat affected zone and its propagate, you see this is a crack, it propagate perpendicular to the what is called weld line direction, that I have written. So, it can take hours of time or it can take some days of times also. So, initially you observe that after doing welding your weld quality is looking so good, but after 1 day or 2 days you observe that oh my god, there occurs some cracking. What I am telling, understand how this cracking is taken place. This cracking generally start heat affected zone and it is propagate transverse to the direction of welding. Okay. That I have written. So, it can take time which can be approximately 16 to 48 hours also. What I am telling, understand. So, the technical community is of the view that it requires all these three factors for hydrogen embrittlement related cracking. These three factors is essential. What are those three factors? Like a susceptible microstructure is required. This susceptible microstructure generally is hard microstructure. This you can say the microstructure of martensite, which is hard microstructure. There should be presence of threshold level of atomic hydrogen. This is another phenomena. Threshold level I have told you. That means, there should be at least some amount, minimum amount of hydrogen should be there, which can have a capability to generate the crack. That threshold, that is why here I have used the term threshold amount, minimum amount of hydrogen is required. If below this threshold value, there will not be what it is called hydrogen embrittlement phenomena or cold cracking. Okay. And another things, there should be also required some tensile minimum threshold, say tensile stress, or you can say well induced residual stress, which is tensile in nature. So, you see, or there can be some externally applied force also. Okay. So, these are the three important factors which are required to generate this cold cracking. Why it is cold cracking? I have already told you, as it is taken place after cooling of the weld specimen, and after cooling also it can take time around a hour or a 1 day, this types of time also it can take. So, these three factors generally require to get this weld embrittlement or hydrogen embrittlement phenomena, or to get the phenomena of cold cracking. What is actually happen in case of cold cracking, that also I will discuss in details.